otherwise you'll never be doing this. But let's say 0 to infinity. So yeah, as long as you have a probability distribution function, you can put minus infinity to infinity. The p will likely be 0 from minus infinity to 0, right? So you can put whatever limits you want. Okay? All right, so in this case, this expression becomes very simple. All it does is it replaces r by r. Right? And this all goes away. Now, of course, there's a very specific reason why that has happened. Why? Can you explain to me mathematically why it turns out the average value of the NPV is simply you just replace r by the average value of r? Yeah?
Because the expectation of revenue is the average revenue.
Well, that's true, but there is something else.
Your average revenue.
Because NPV is linear in R. Okay? Does it make sense? Now let's do another case. I'm not going to write it down in boring details, but I'm just going to first talk about it and then. So now let's say that you have, so because NPV is linear in R, you can simply replace r by r bar. Now let's consider a case where not just revenue is uncertain, but also COMD is uncertain, which actually is also quite likely. So in that case, I'm not going to write it down in details, but you can see that if you have integral something, let's say NPV. So now in this case, you'll have a double integral. You'll have probability of revenue and the probability of COMD. So you know you need both probability distribution functions, and this will get replaced by a double integral. Now the assumption we are implicitly making there is that these two probabilities are completely uncorrelated. Okay? And that actually again is a reasonable assumption because the probability distribution function for revenue, the uncertainty there is coming from the cost of what you're trying to sell, and the probability of COMD is coming from utilities. Now you could certainly make an argument that, well, what will actually happen is the cost of utilities in general will reflect in the cost change in everything, so the two are actually correlated, right? And that actually is a correct statement. But to leading order, at least for simplicity, let's assume that these two aren't correlated. So this is how, so now you have a double integral. Okay? Now if you're double integral, that actually also doesn't make this any complicated. Because you can see there is no term including product of R and COMD. So you'll have basically, so when you're doing this type of analysis, you'll have three types of terms. One is a term that doesn't depend on R, doesn't depend on COMD. So that term multiplies probability of R, probability of COMD, D R, D COMD. This thing can be taken out, and this probability, because the two are completely uncoupled, this can be, because this probability does not depend on CMD, this probability doesn't depend on R. So you can write this as an integral of P of R dr times integral of P of COMD d COMD. Right? Does it make sense? Because of the two variables of integration are completely uncoupled, you can split that double integration into a product of two single integrations. In which case, you already know what this is, right? That is 1, and this is also 1. So you can see the variables that do not depend on R, do not depend on COMD, they stay as they are in the beginning. Nothing changes, right? Then there will be a variable that will depend, let's say, only on R. So we're going to remove this now. If it depends only on R, then this integral, so let's say there's something times R, right? So you can split that as there will be R here and be nothing here. So this integral will still give you 1, and this integral will give you R bar. And then you can look at the same way for COMD. So you can again argue that even in this case, nothing really changes. All that happens is R gets replaced by R bar and COMD gets replaced by COMD bar. right? Still really no significant complication. Make sense? All right. Now, can you guys give me an example from this problem? Give me two variables, and if those two variables are uncertain, the problem will not be linear. It will not be of the type that we just discussed.
I.
Very good. If I is uncertain, then actually the problem is non-linear to begin with. It doesn't even matter. You don't even have to have find 2. Right? But I, you could argue, is not really non-linear because I is something that the company has decided. Right? I is basically the rate at which you want to make money. So, in reality, of course, everything is uncertain, but you could say that I is something, it's a benchmark of the company. So remember, all this analysis being done before the company's actually even started making anything. So I is just the rate the company wants to make money. But in reality, but you are right, that if I is uncertain, then the whole problem becomes non-linear to begin with. You have to do integration on I. But tell me something else. Give me not I, but some other variable. Give me a combination of two variables. If both of those are uncertain, then yeah, this becomes a non-linear problem. Yeah?
Tax revenue.
Very good. Tax rate and revenue. Now, I don't know about tax rate, and I did say we're not going to talk about politics, but I guess we cannot escape that. But certainly, tax rate can change, right? So I think that's not a bad assumption that yes, the tax rate can change, and of course, revenue and CUMD can also change. So now, if that is the case, then you will see that the problem is no longer as simple. So now we are going to assume that tax rate is uncertain and also revenue is uncertain. So in that case, you can see the only term, there's really only one term that you really have to handle more carefully. The rest of the terms you already know what to do with, right? Rest of the terms you know, if the term doesn't have either T or R, replace it by just itself. If there's something having only T, replace T by T bar. If there's something only R, replace it by R bar. So the only complicating term is going to be TR. Right? All right, so then we have to basically look at this term TR times the probability P of, in this case, let's say, yeah, P of R times P of P. Okay? All right. But again, as we discussed earlier, if revenue R doesn't depend on T, right? And the probability for R doesn't depend on T either, then these two integrals can still be separated into a product of two integrals. Right? If the probabilities are completely uncoupled. In that case, you can see this will still break down to a product of two functions, and that will simply be T bar times R bar.
Wait, is that a case for when P is a function of R and T? Or no?
P is a function of R and T, yes. But we are assuming that it can be broken up into a function of R and a function of T. If that assumption is not true, then yeah, this cannot be done. You need to know what the probability, so the probability in reality, what you have is a probability function of R comma T. This is what you need to know because both are uncertain. So essentially a probability distribution diagram is like a three-dimensional diagram.
So you're
But-
saying if the probability density function is separable,
Yeah,
then it's fine.
yeah, then you can still do it. And that again is a reasonable assumption. You could argue, again as I'm saying, if you really start thinking in details, I think when it comes to money, everything is so interlinked that all probabilities almost certainly are going to depend on each other, right? But as a reasonable approximation to say that, yeah, the tax rate and revenue are sort of two different things, then we can assume that to be uncoupled. Okay? So right now we are only discussing this conceptually. Okay? because we haven't, and now I'm going to start talking about some reasonable estimations of probability distribution functions. Okay? Everybody's good so far? Okay, so now actually I'm going to take a step back and not talk about NPV, but I'm going to talk about something slightly different.
Can we do some examples?
Sorry, yeah, we're going to do an example here. Not of NPV. I mean, NPV in some sense, we can see things are not that interesting in NPV because everything just gets replaced by the average values. But I'm going to do an example that I told you in class earlier, but today I'm going to actually do it. So the example I told you a while back is that, let's imagine that there's a company making fertilizer, and from the exhaust of the fertilizer, you actually have a gas stream containing ammonia, right? So let's say C, or let's say C is the concentration of ammonia in this exit stream. Okay? Now, OSHA requires that this concentration be below 25 ppm. Actually, 8-hour exposure is 50, but 25 ppm is toxic limit. So let's say the company has to keep this concentration below 25 ppm. And this is given by the regulatory agencies, right? Okay, but the problem is this, if you obviously got to design this plant, right? You can design this plant to target 25 ppm. Is that a good idea?
No.
Why not? Very good, because if there's the slightest of problem, your concentration will exceed 25 ppm, and then let's say the company has to pay a penalty. So let's say that there is a continuous monitoring of this concentration, which in reality never happens. There's never a continuous monitoring. But let's just say there is a continuous monitoring and the company has to pay a penalty, which depends on, so the penalty, now there is a huge penalty, okay, but the penalty is not, it's not continuous monitoring usually. So let's say the penalty is some function of C minus C safe. Okay? So CS is a safe limit of ammonia less than